Hello everyone, my name is Yaroslav Golubev. I am a researcher at JetBrains Research, and I would like to tell you about our work titled PyNose, a test smell detector for Python, conducted together with our colleagues from the University of California, Irvine. Code smells are an important concept in software engineering. They represent certain bad design and architectural choices that can lead to problems with maintaining the project in the future. Test code has its own variety of code smells, called test smells. Such smells can affect the test code itself as well as the production code that is being tested. Research shows that test smells also have the negative effect on the projects they are encountered in, making the code less readable and more error-prone. However, the existing research focuses on traditional languages like Java and Scala, as well as Android projects. At the same time, Python is growing in popularity with each year. It is especially popular in such crucial areas as data science and machine learning. For this reason, in our work, we strive to extend the existing research to Python, detect and analyze test smells in it. To do that, we perform several different steps. Firstly, we need to compile a list of test smells to detect. In our work, we do it in two ways. We perform a small-scale systematic mapping study to select test smells that were already described in literature, and we also search for Python-specific test smells by studying popular changes in mature Python projects. Then, we need to develop a tool that would be able to detect all these test smells. In our work, we present PyNose, a plugin for PyCharm that detects 18 test smells. We also manually validate the performance of PyNose on a small dataset of projects. Finally, in the last part of our work, we perform the analysis of test smells in the Python projects. We analyze the prevalence of different test smells in Python projects, as well as their co-occurrence. Now, let's discuss all this in details. We start by compiling a list of test smells studied in the literature. The search question for our mapping study was what test smells have been studied in the literature to date. A pilot study on two digital libraries resulted in this simple search string that we used. We searched for papers in three different data sources: ACM Digital Library, IEEE Explorer, and Scopus. The initial search resulted in 54 publications. To narrow down the search, we applied the inclusion and exclusion criteria presented on the slide and conducted a single iteration of backward snowballing. In the end, the search resulted in 29 different publications that describe a total of 33 different test smells. You can find the full table of papers and test smells in our supplementary material by following the QR code. However, not all of these test smells could be implemented. Some test smells that were introduced for Java are just not applicable for Python, which can be due to differences in grammar or specific conventions. Some test smells rely on production code that is being tested. Overall, automatically mapping test methods to production methods is a challenging task, so we leave such test smells for future work. Finally, some test smells require us to actually run the test case. We plan to implement the detection as a static analysis tool, which is why we left out such test smells also. In total, we selected 17 diverse test smells. You can see their full list on the slide. During this selection, we also decided to focus specifically on the unit test testing framework. The reason for that is that, firstly, this is the default and one of the most popular testing frameworks, and secondly, that it is largely inspired by Java's JUnit, making it simple to migrate certain test smells from Java to unit test. We plan to support more frameworks in the future. You can find the detailed description of the test smells in the paper. Let us now describe just several most popular ones to give you an idea about them. Assertion roulette occurs when a test case has multiple non-documented assertions. Multiple assertion statements without a descriptive message impact the readability, understandability, and maintainability, as it becomes more difficult to understand the reason why this test fails. Conditional test logic runs against the rule that test cases need to be simple and execute all statements in the production code. Conditions within the test case alter the behavior of the test and lead to situations where the test fails to detect defects in the production code under some conditions. Another example is a magic number test. It occurs when the assert statements in a test case contain numeric literal magic numbers as parameters instead of more descriptive constants or variables. The proposed test smells are all studied in the existing literature. However, they were proposed for other languages. It is reasonable to assume that Python has its own test smells. To discover them, we used a tool called Python Change Miner that we developed to detect frequent code change patterns in Python projects. The tool uses a special graph representation of code. You can find more details about it in our previous paper by following the QR code. The idea behind this is to see what changes occur frequently in Python tests and see if some of them can be considered as fixing or introducing a test smell. To detect change patterns, we collected a dataset of mature Python projects. The dataset includes 450 projects that we selected from GitHub by using the presented criteria suggested in literature. We will refer to this dataset as primary. You can find the full list of projects in our supplementary materials. We traversed the version control system history of all these projects, detected all changes to Python files with the word test in the name, and searched for change patterns in them. Overall, Python Change Miner was able to detect 8,239 different change patterns among the test files in our dataset. 652 patterns were cross-project, meaning that they occurred in at least 2 different projects. 159 patterns occurred in at least 3 projects. For practical purposes, we decided to manually study only these 159 patterns, since they can be considered more universal. The authors of the paper manually analyzed all the patterns and classified them. We noticed that as much as 44% of all the patterns are related to changes to the assertion logic. All authors came to the conclusion that potential test smells can only occur within these patterns, since other changes like logging, data structures, etc. are not really related to tests. When looking for possible test smells, the authors considered the code of the change as well as the commit messages. Here is an example of a change pattern that occurs in 7 different projects. This can give you an idea of what a change pattern looks like. Let's now see how developers change the assertions. Some of the changes to assertions change the logic of testing. For example, it is possible to relax the condition from strict equality to a regular expression to make it more permissive. Or, on the contrary, it is possible to go from checking none to checking a new specific class to make the comparison more precise. Such changes are interesting, but they cannot be considered as fixing a test smell because they change the behavior of the code. However, not all changes alter the logic. This is the same example we saw in 7 different projects. It goes from checking the truthness of an in statement to using a specific assertion for it. It is very important to consider the corresponding commit message that describes that this change allows to make the results clearer in the case of a failure. In that sense, this can be considered as fixing a test smell, since the logic remains the same, but the code becomes easier to understand and interpret. In the other case, that occurred in several projects, a truthness of a comparison is changed to another specific assertion. Overall, we propose to group various such cases into a single test smell that we call suboptimal assert. This test smell represents various ways to write assertions that are not optimal when a better and a clearer way exists that can make the code easier to read. You can find a list of all test cases that we encountered in the supplementary materials. In the second part of our study, we implement PyNose, a tool for detecting the described 18 test smells, 17 from the literature, and suboptimal assert. We developed PyNose as a plugin for PyCharm, a popular Python IDE developed by JetBrains. This allows developers to detect test smells from the comfort of their usual editor. It also allows us to use the inner representation of code in the IntelliJ platform that PyCharm is based on. PyNose works in 2 different regimes, with a user interface, straight in PyCharm, or from the command line, where the plugin launches an instance of PyCharm in the background and detects test smells without the full opening of the project. In both cases, firstly, the necessary project is opened, then all Python files are parsed into a special representation. In this representation, their PSI trees are parsed to detect all test suits and test cases. PSI tree is a specialized type of a concrete syntax tree used inside JetBrains IDE. The PSI of each test case is analyzed to detect all the supported test smells. Finally, the results are presented to the user. If the plugin was used in the IDE, then the test smells are listed in a special tool window. If the plugin was run as a command line tool, then the results are saved to a JSON file for further analysis. The detection of specific test smells is implemented in the same way as they are detected in the original papers. For example, for the magic number test, we find all the assertions and check that one of the arguments has the type literal in the syntax tree. To assess the performance of PyNose, we conducted its manual validation. We collected a small dataset of 8 projects And the three authors of the paper independently labeled all the test files in the projects as having specific test smells using their definitions. The authors then discussed their labeling until they reached consensus. After curating this dataset of labeled test files, we launched PyNose on it and for each test smell calculated its precision, recall, and F1 value. It can be seen that overall, PyNose shows good results with metrics of about 95%. You can find more details about the reasons for existing errors in our paper. Comparing with the state-of-the-art test smell detection tool for Java, TS-Detect, we can see that PyNose shows similar performance. In the final part of our study, we conducted the analysis of Python projects from the standpoint of test smell prevalence. We conducted our analysis on two datasets. Firstly, we used the same primary dataset that we described above, since it contains a lot of mature Python projects. However, since the history of these projects were used to obtain our suboptimal assert test smell, we also use another, secondary data set as control. It is collected using the same criteria, only with fewer comments. You can find the full list of projects in our supplementary materials. We compare the prevalence of test smells on the level of test suites and projects. Overall, 248 projects out of 450 use unit test, indicating its popularity. It can be seen that the number of testing entities in different mature projects can differ significantly. This figure shows the overall distribution of test smells among all projects and among all test suites. Firstly, it can be seen that the results are similar for both datasets, so we can use the results of the primary dataset presented in blue. It can also be seen that test smells are very popular in Python. Only 5 projects in our dataset had no test smells, and they were really small projects with about a dozen of test cases. The most popular test smells, assertion roulette and conditional test logic, occur in almost 90% of the projects, and assertion roulette specifically occurs in more than half of all test suites. On the other end of the spectrum, some test smells are extremely rare, like empty test, construction initialization, and default test. Finally, suboptimal assert, newly added test smell, seems to be an important addition to the list, as it occurs in more than 70% of projects. However, the distribution of test smells considers them separately without actually conveying how smelly the tests are. What is important is how test smells coexist with one another. This figure shows the distribution of the number of different test smells among test suites. It can be seen that only 16% of all test suites are free from smells. The remaining 84% have some, at least one smell. About 23% have exactly one smell, 20% have two smells, 16% have three smells, and this number gradually decreases with the number of co-occurring test smells. The highest occurring number in the primary dataset appears in a single test suite with 12 distinct test smells. This figure also sheds a new light on the prevalence of test smells in Python code. With more than half of all test suites having two different test smells or more, their effect on the maintainability of code can become more complex. Let us conclude by discussing the possible directions for future work. Currently, we are already working on extending the functionality of PyNose. This includes adding the support of PyTest, another very prominent testing framework for Python, adding better user interface in the plugin regime, highlighting the smelly parts of test suites, configuring test smells detection with finer detail, allowing you to detect only certain test smells and configure them, and supporting more test smells. We also plan to conduct an analysis of Python projects on a larger scale, as well as to compare the distribution between projects in Python and in Java. On this slide, you can find QR codes with links to the preprint of our paper, the tool itself, as well as the supplementary materials. Thank you very much for your attention.